Good afternoon, everybody. My name is Kathy Schultz, and I am the Water Education Specialist with the California Department of Water Resources. Welcome to Water Wednesday. The mission of the Department of Water Resources is to sustainably manage the water resources of California in cooperation with other agencies to benefit the state's people and protect, restore, and enhance the natural and human environments. Since next week is Flood Preparedness Week, we are currently talking about flood risk and how DWR and countless other agencies and institutions work to protect people and cities and infrastructure from floods. This is the third of our fourth presentation on this topic. Our past two speakers discussed how we use engineering and natural systems like floodplains to manage that flood risk. And if you missed their presentations, you can always find them on our DWR YouTube page. Today, we are joined by Alyssa Lin, DWR's Climate Change Program Manager. There she is. Hey, Alyssa. And
hi, Kathy.
Hey. Both of our previous speakers mentioned atmospheric rivers when they were talking. And that's because you can't really talk about flooding in California without mentioning atmospheric rivers, or ARs for short. And Alyssa is here today to tell us more about these, how climate change is impacting them, and about some really cool research that's being done to better understand how atmospheric rivers form, how they move, and hopefully reduce our risk of flooding. Before I turn things over to Alyssa, I just want to go through a couple of really quick logistics. If you are joining us on Zoom, we've asked you to turn your cameras and your audio off. This just helps avoid distractions and barking dogs, things like that. But we really do want to hear from you. This is designed to be an interactive experience. And so if you have questions, please feel free to submit them in the chat box. You'll want to send them to me. And when Alyssa's done with her presentation, we will get to as many of those questions as possible. The program comes with closed captions, so if you want to see what's being said as we go along, you simply go down to the bottom of your screen, and that's where you'll find the chat box as well. The chat box is just a speech bubble with the word chat under it. The closed captions is a little rectangle with CC in it, and you can either turn the captions on or off that way. And that's pretty much it. We really appreciate you joining us here today, and I'm going to turn things over to Alyssa.
Thanks, Kathy. I'm really glad to be here to join you guys. I'm glad to share some science facts about our weather and climate in California. Sometimes it can get quite extreme, so today we're going to talk about that. Also, I've been researching these topics for about 30 years and explaining them, so hopefully I can answer some of your questions you might have. They're very interesting topics. And we're going to talk about how big storms form and what we can do about them. All right, I'm going to try to bring up my slides. Hopefully this will work. Okay, so California climate, climate change, and atmospheric rivers. Let's first talk about the precipitation that we have in California. On the left, there's a map of the state. Maybe you can kind of identify where you live in the state and think about what the color scheme that's in your area means for your precipitation. What do we mean by precipitation? We mean the water that falls from the sky. It could come as rain or snow if it's cold, sometimes hail or ice if there's a big thunderstorm. Hail and ice are more common in the Midwest, but we can get thunderstorms that produce that type of precipitation as well. We certainly get lots of rain and snow over time, a little less snow than rain. We'll talk about that in just a minute. So we have a Mediterranean climate in California that brings us, we have very wet winters and cool winters. So if you've lived here a few seasons, even you kids probably know that we really only get that rainfall or those storms in the winter. Most of the summer, it's usually very warm and very dry. The precipitation really varies across the state. So on the left, you can see the inch variation. The amount of precipitation is really variable. Very far up to the north, the top left of the screen, the blue zones, those are over 100 inches of rain per year. Whereas down towards the lower part of the state, the southern part, where it's very dry, you may have heard of Death Valley, the rainfall may only be about 5 inches per year. But either way, that rainfall usually only happens in the wintertime. Pretty rare to see summertime storms. There's also a lot of year-to-year variability. By that I mean each year can be very different. Some years very dry, some years very wet, You've heard about drought. That's when we have several dry years in a row. So we'll talk about what causes some of that year-to-year variability coming up here in just a minute. And interestingly enough, it's only a few storms per year that really give us all of our precipitation in that amount of time. It's maybe only 5 to 10 days, and a lot of those storms can be what we call atmospheric rivers. Great name. Is it a river? It is. It's a river up in the sky, a river of moisture. So it's only a few days per year that we really end up seeing all the rainfall that we need for our water supply. So how does this happen? We're going to talk a little bit about the location differences. That map showed a lot of different places with different type of rainfall or different amounts. Well, when the air comes in off the Pacific from the left and runs into a mountain chain, like we have a lot of in California, including the Sierra Nevada mountain range, what happens is that air streams in. Those blue arrows are showing the onslaught of the airflow from the Pacific Ocean, so from the west, from your left. That air slides and moves into a mountain range, and it has no choice but to rise up. When that air rises, it condenses, it forms a cloud, it cools off, and then we end up with a cloud. And that cloud causes precipitation. If it's cold enough, if the temperature is below 32 degrees Fahrenheit, we get snow. If it's warm, we end up with rain. But either way, all that moisture is squeezed out of the cloud formation. And on the other side of the mountain, now we're at the top of that ridge where the arrow is turning to red. Everything in that continuing direction there in the red is very dry air. The moisture's gone, the air starts to sink. And sinking air doesn't produce a cloud. It's the opposite of the other side. That blue side, the left side, is where the cloud is forming and creating precipitation. On the opposite side, or in this map, it would be on the Nevada side toward Reno, the air gets very hot and dry. They have a lot less precipitation on that side. All over the state, wherever the wind is flowing into a mountain range, you're going to end up with precipitation forming. We call this orographic. New word for you, new vocabulary word, orographic. It comes from the Greek oro, which means mountain. So that's where the origin of that word actually comes from. So this type of orographic precipitation, this is the kind of precipitation we have in the state, mainly because of all the mountain ranges we have. We also have differences in the timing. When does that rain fall? There's a lot difference throughout the year. We don't have the same amount of precipitation in each of the months, getting back to what I said about the Mediterranean climate. So let's start here at the beginning of what we call a water year. Starts October 1st. So we're going to go clockwise around the monthly chart, around this water year through the year. And October doesn't have much, about 6% of the precipitation, November 13%. And again, we're going up and down, up around clockwise fashion. Look at those three big months, December, January, February, 17, 18, and 16% of precipitation. They're very similar to each other, but in total, those 3 months bring us the bulk of the rainfall or snow that we're going to see for a whole year. So those are our critical water supply months. Some of it can fall as snow, which will be held as snow in the Sierra Nevada till it melts. Some of it can be rain, but those 3 months are really critical. If we don't have rain or snow, we don't have enough storms in those 3 months, it's very hard to make up for it. Because you'll see as you continue the rest of that water year, March about 14%. Some years you could have a great March, but sometimes it can't make up for any loss you had in the winter. April about 8%, May only 4%, and June, July, and September just a couple percent. Usually those are storms that hit the mountain ranges and not the coast. So we have a lot of monthly difference. And we also have yearly difference in our temperatures. So another aspect of our climate in California is our temperatures. What you're looking at here is a chart of the temperatures in California, the state average, since 1895. The line across the middle, the horizontal line upon which those blue and red bars are all standing, that's an average, if you will. The red years are the warmer years. The blue years are the colder years. If you'll notice from this chart, the red years, the warmer than average years, are really more in the last couple decades. They're much more common right now or lately than they had been in the past. The cooler than average years are on the left, or sort of in the olden days. There was a while there where we had cooler than that average for quite some time in the early part of the last century, in the early part of the 20th century. But now we're starting to see warmer years. And the warmer years overall really do impact the type of precipitation we get in the state. So what is it that's happening to our temperatures? We're going to talk a little bit more about the whole Earth, not just California. Of course, what happens on Earth affects us as well, affects everybody. And we have something called the greenhouse effect, you may have heard of. Greenhouse gases are part of our atmosphere. And what happens is that layer of the atmosphere, the gray layer over the Earth, where the orange arrow is kind of bouncing up and down, that's our atmosphere, a thin layer of atmosphere, a shell of different types of air. One of the things in that atmosphere is carbon dioxide. And those greenhouse gases, oh, it's called CO2 on the screen there. CO2 and other gases in the atmosphere trap the heat. What do we mean by that? The sunlight comes in, shines on the Earth, but it doesn't all just go back out into space. Not all of it. Some of it turns into heat and is trapped in that layer. The more carbon dioxide you have in that layer, the more heat you end up trapping and the warmer it gets overall across the whole globe. Kind of on average, a little bit of a change in our temperature thanks to that. And so the burning of our fossil fuels contributes to the amount of carbon dioxide in the atmosphere. The more we burn, the more carbon dioxide we have. It's been building up for a while, and that is called the greenhouse effect. So what does that mean for our climate in California, or any climate, if we have a shift in our climate to a warmer regime? The curve shows our climate with an average temperature kind of in the middle, a bell curve. Most of our temperatures are somewhere in an average zone. For California, that might be high temperatures, 60s to the 90s on average around the Sacramento area. Then we have days that are very, very cold, or mornings that are cold, and some heat spells. Well, if you slide the entire curve over as you increase your average temperature, that whole curve is going to shift over to the warmer side. So all the days may have a slight increase in temperatures, or just some of the extremes might get more intense. You'll end up with less cold spells. You'll still have them, but fewer of these cold spells because your curve has moved over into a slightly warmer temperature regime. You'll have hotter weather and more extreme hot weather. See the tails of that curve, now that they've shifted over to the hotter, our extreme hot conditions become a little bit more frequent and more dangerous because humans are very susceptible, obviously, to high temperatures. So are plant species and animal species. So with that warming that's going on, what would that mean for you in your hometown? Let's bring it back to something that's kind of local. Oh, I skipped a slide, I'm going to go one. Here's Sacramento, on average, with a temperature of 61 degrees Fahrenheit. That's the red dot in the middle. That's the capital city. What if we were to see an increase in 4 degrees Fahrenheit or 2 degrees centigrade? And why is that important? Well, we'd like to keep our warming below 2 degrees centigrade to prevent irreversible climate change. But if we did get to that 2 degrees centigrade, what would it feel like in Sacramento? Just to change your average temperature, oops, sorry, screen went too fast there. If we went up those 4 degrees Fahrenheit, that would be what it would be like to live in Bakersfield. Now, if you've ever been down to Bakersfield, you know the Central Valley is a lot hotter on average. You feel it. The heat waves are hotter and higher. And if it was 7 degrees warmer, Sacramento would feel like Las Vegas, Nevada. And 12 degrees warmer in Fahrenheit, it would be like Phoenix. And Phoenix is setting a record this year with number of 100-degree days. So climate change will actually be felt. You'll just kind of notice that suddenly it's a lot warmer more often. What do the temperature changes mean for our water resources in California? The graph on the left there shows you a lot of different impacts, and I want to talk about what some of those details are. It means that we'll have less snow and earlier spring runoff. And the runoff is the stream flow, the amount of snow that melts down into our rivers and comes down off the mountains through the spring and the summer when we really do need it. So there's less snow, comes out earlier, could mess up what we're able to capture and save and use. There's also the problem of sea level rise. As the air temperatures rise, so do ocean temperatures, and that'll raise the level of the coastal oceans. We'll have more severe storms with the potential for flooding. We're leading into flood preparedness next week. So we want to tie this to flooding. And those warmer temperatures do contribute to the risk of flooding. We'll have more frequent droughts with the higher temperatures. And there's also increased water demand for crops, the environment, and cities and people. Everyone needs more water to stay cool, stay hydrated. And this leads to too warm water. The water gets too warm for cold water fish like salmon and steelhead. So those temperature changes do impact, because of climate change, they impact the water resources that we have as a state. Now, how does this actually happen? What are our biggest storms? The map at the top shows a moisture plume coming across the ocean into California. You can see on the left side of the black area of North America, that's California. So those colored bands, the green, the orange, the yellow, is pointing right at California. It's coming from the tropics. That's moisture. And about half of our annual precipitation comes from these atmospheric rivers, ARs. And flood damages from one atmospheric river can cost up to $20 million. Climate change is projected to make them stronger and make floods bigger. So we do really want to get a handle on these storms. So what do? Its atmospheric river brings moist air from the Pacific Ocean, which is on the left side of your screen, right towards the California coast. Remember that map that I showed you before, the little chart of the type of precipitation this is called? Maybe you can remember the weird new word. As the air rises, the water vapor cools and it forms a precipitation on that windward side, on the California side. We call that orographic. The atmospheric rivers are really pronounced. They're really strong in this orographic effect. The mountains really impact what an atmospheric river can do. Now, atmospheric rivers don't just happen here. Here's a global map, all the continents, and showing all the places where we've discovered as researchers that these atmospheric rivers occur. There's California. That's a little blue sector there, the United States and North America. So there's us. That little section to our left, that red zone, that's where the atmospheric rivers that hit us originate. But they happen all over the world, so it's not just here in California. They occur all around the globe, and they're responsible for most of the water vapor transport across the earth. So let's learn a little bit more about these. What is an atmospheric river? Why are they so important? Maybe you have some idea already. And how can we forecast these to help protect lives and property? On the right there, that's a satellite image. Now that's a satellite picture you might see during the news of the clouds and a storm that's coming toward the coast. That swirl of clouds, that big comma, that can be an atmospheric river. They're not that dissimilar in the sky. They're not as round as hurricanes, but they can be quite powerful. So I'm going to turn it back over to the DWR offices to share with you a video on atmospheric rivers from the Scripps Institution of Oceanography.
Imagine a river in the sky with more than twice the water of the Amazon. It's called an atmospheric river. Atmospheric rivers are long, narrow bands of concentrated water vapor that produce major amounts of rainfall. Atmospheric rivers begin in the warm waters of the Pacific, where water evaporates into the air. When this humid air meets a Pacific storm, the water vapor is concentrated and driven toward the coast, becoming a fire hose of rainfall and wind. Once the atmospheric river reaches the coastal mountains and the inland Sierra, the collision squeezes additional rain and snow from the system. Atmospheric rivers are responsible for up to half of California's annual precipitation. Scientists at Scripps Institution of Oceanography have developed a new system that rates atmospheric rivers on a scale from 1 to 5. The rating system helps identify atmospheric rivers that are beneficial, such as those that replenish reservoirs, and ones that produce hazards like flooding. Understanding atmospheric rivers is key to improving weather forecasts for better managing water resources and predicting flood risk.
Great. So that scale they talked about is very important. This is how we're going to help communicate as scientists to the public to be prepared for these big atmospheric river storms. You've heard of a hurricane scale. Its name is the Saffir-Simpson scale, but you've heard of it, probably Category 5 hurricane, Category 4 hurricane. Well, we've developed, DWR helped contribute to the research with Scripps and other scientists to develop a scale for the intensity of these types of storms. Atmospheric river 5s are the most hazardous. That would be a red color. And they go all the way down towards a blue atmospheric river, which may be very beneficial. It may not be so windy that it causes a great deal of damage. It may not cause flooding, but maybe it's got a good shot of rainfall and moisture to help replenish the reservoirs. So they range from beneficial to hazardous. And hopefully over time, you'll start to hear about these on newscasts and whatnot to be able to prepare for what type of an atmospheric river may be coming. So it's important for researchers to know what is on the way, what's coming off the Pacific Ocean, because these storms can be very costly and damaging. That's a picture of the Russian River. All of that is water. Sure, on the right side of the picture where the river is, you're supposed to see the water, but it's very turbulent because it's so brown. But look at how much of the rest of the area is just inundated with water where there shouldn't be. Anything in the rest of the screen that doesn't look like it should be the river, that's where the water's gone where it shouldn't. And that's when you're in bad shape. And the Russian River is very prone to these atmospheric river type flooding events. All 7 of their floods within 8 years were caused by atmospheric rivers. They cost an average of about $28 million per year. Some years we don't get money, some we get too many. So what do we do about this? We actually put together a set of new Doppler radars. That's me in front of a new Doppler radar system that was deployed out in the Bay Area of California to see what's coming off the Pacific. How strong are they? How much moisture is inside them? How long are they going to last? So we use the radars to track our atmospheric rivers to help us prepare for the storms that are on their way in. Again, with flood preparedness week next week, we want to know what we're doing about it. So atmospheric rivers, they're a valuable component to California's water supply. They can lead to expensive and damaging floods, but improved observations, forecasts, and models are helping us prepare for all of these storms. So I want to thank the DWR Water Wednesday folks, and I think we're going to be able to take some questions from you guys.
Great, thank you, Alyssa. So the first thing I wanted to ask you is, can you tell us a little bit more, how does that radar system work?
Sure. Doppler radars are interesting, and I want to explain what makes them Doppler from a regular one. But first of all, what does a regular radar do? You have to put up a giant piece of equipment that sends out microwaves. Not microwaves like you cook with necessarily, but they're close to that wavelength. And these microwave beams go out into the atmosphere, into the sky, and they are going to keep just going right on out into space unless they hit a raindrop. So all of the raindrops inside a cloud, the back of those raindrops will reflect the signal back to the radar. So what a radar is doing in essence is sending out a signal, but mainly measuring what's coming back towards it. That means it's hit a raindrop. That means there's something there that is providing a signal to them, and the Doppler radar knows that's where the rain is located. And why it's called Doppler is that Doppler effect is a shift in the wavelength. So when those wavelength microwave energies come back to the radar, if it notices a change in the wavelength that's returned, it means that the raindrop is either going away or towards the radar unit. So the Doppler will tell you not just how much the rain, how much and where the rain is located, but also whether it's moving towards you or away. And you want to know, obviously, if it's coming towards you, because then you're going to be impacted by the storm and we can track them. So a whole new set of these Doppler radars and other important scientific measuring instruments have been put up over the last few years along the coast of California to give water managers and everyday citizens a better idea of how big the storms are and when they're coming.
So when the radar hits it, if it's a bigger storm with more raindrops essentially in it, you're going to get more waves bouncing back at you.
Yep, and echo is the word for that. You get more echo, just like you would think something bouncing back. It's an echo, and that's what you see.
All right. And by putting them out, you mentioned this is a new series out by the coast. Does that give us the ability to have a sense of how big these atmospheric rivers are before they arrive?
Yes, and of course, you're looking out into the ocean and there's no one out there to tell you. By that, I mean, like if you live in the Midwest, like in a state like Illinois, pretty easy to know what weather's coming because you've heard reports from Iowa or Nebraska, things that are further west. But here we're right on the edge of the coast. The satellites that we had, initially the satellites that were deployed, 20, 30, 40 years ago or so could give you pictures of the clouds, but that's not very helpful. You need to know more of the details of what's inside there. So we use the radars for places that there aren't normal observations. We don't have a lot of weather balloons going up from standing people across the Pacific. So we really need these radars, and that's why they've been enhanced and improved to give a better idea of the timing and the size.
Great. We have a question. What are the conditions that make an atmospheric river stronger or weaker than another?
Aha. So that gets back to the origin, the location where they start. And for us, it may be towards somewhere in, say, Hawaii. Let's call that for an example. In the Hawaii area, the amount of moisture that gets caught up in that cloud plume, perhaps the temperature of the ocean will produce more water vapor, maybe the wind current itself or the ocean currents, which actually do have an effect on where the jet stream carries these low pressure cells. So all those factors, including the winds and the amount of moisture, We call it integrated water vapor. How much water is in that column? And then how fast is that giant hose? That's why it's called an atmospheric river, like that hose of energy. How quickly is that coming towards you, and how long is it going to last? So the duration of the atmospheric river also plays a big role. If it's going to be over in 2 hours, I mean, that's bad, but it's certainly not as bad as something that's going to last 12 or 16 hours. And when you really get in bad shape with the atmospheric rivers is if they last for a good deal of time, maybe 16 hours or so, and then another one is right on its heels. Maybe there's a break, and then there's another atmospheric river that comes in. And interestingly enough, on the opposite side, in order to get out of a drought, if we're in a period where we've had a few years in a row without enough precipitation, or this an average amount, let's say, if we just are on the dry side for quite a while, in order to get out of a drought, it takes atmospheric rivers. It won't happen with the cold Gulf of Alaska storms. We can get a different type of storm. There are other kinds. It's not just atmospheric rivers that hit us, but the atmospheric rivers really bring the moisture that can help end a drought.
Okay. All right. And then the danger when one comes in on top of the other is that that water just doesn't have somewhere to go, or it can't be absorbed by the ground, or
That's right. If the ground's already saturated, especially if you had a couple, or if you're in the middle of winter, everything's already wet anyway. So the back-to-back series of atmospheric rivers is when we've really seen the bad floods occur.
I've got time for probably 2 more questions. There's a question here. I don't know if you remember your slides exactly.
Okay.
There was a pink AR labeled as December 11th, and somebody wants to know if it was stronger than the red AR.
Oh, that was probably back to the chart about with the color coding. And after the video that showed the new scale, the AR levels,
Right.
I showed a figure that had a picture of a map with all the arrows coming in. And those were showing the different types of storms. And that particular year, I think on that chart, it was 2017. But what we do as scientists is show the position that the atmospheric river came from in that diagram and the strength of the atmospheric river, and then label the ones that are red as the strongest of that particular year. And some of the moderate ones, have different color coding. So I hope that answers the question. But yes, we do track that. I helped kind of develop the first schematic of something like that long ago on literally the back of an envelope kind of piece of paper to get an idea for which storms were coming from what direction and had the longest duration, and then may have led to the most damage or created the most precipitation.
Okay, great. Then one final question. You mentioned that the atmospheric rivers, they kind of spin like hurricanes, but they don't form into that full hurricane with the eye of the storm. With climate change and the warming of the oceans, could we get hurricanes in California?
Well, they wouldn't be exactly hurricanes like you'll see in the Gulf states. Those are formed over very warm water, like 80-degree temperatures, and obviously they're very, they could form a complete circle, whereas ours usually don't wrap all the way around. But our winds can be just as strong as in a hurricane, maybe not for very long, but we can definitely get over 60-mile-an-hour winds. And in the Sierra, those winds can gust over 100 to 120 miles an hour during the really strong storm events that hit. But what climate change and projections tell us is the atmospheric rivers are going to get stronger. They may or may not become more frequent. The timing of them is tough, and so we could still have very dry years without the atmospheric rivers. But it does look like what we're going to see is, oops, sorry, I'm not showing my slides again, am I? Didn't mean to. But what we do anticipate, though, is that the strength of the atmospheric rivers when they hit, because it's warmer, they'll be bigger. They'll be more, the air can hold more moisture when it warms up. So overall, the whole Pacific Basin, as it warms up, it has the possibility to create larger storms. And so in some sense, even though they're not the same as a hurricane, they are as good as it gets for a hurricane for us on the West Coast. They have a lot of equivalent damage.
Great. Well, not great actually, but so given that and given that climate change is happening, but there's still time to reduce the intensity, what are some things that people who are watching today can do to help slow climate change or be better prepared for these larger ARs that are potentially coming?
Sure. So there's some things that we can do individually, and there's some things we sort of have to do as a society all together. And the first things that you can do just on your own, you've probably heard of some of these. They fall under the category of mitigation. And in climate change, mitigation means to reduce the amount of greenhouse gases that we're helping contribute to the atmosphere or emitting. So what you want to do is try to find some renewable energy sources. Maybe you're lucky enough that your family or your parents' business or someone can use solar or wind or hydropower. Any power that is not based on fossil fuels will help. You'll also want to turn off the lights, conserve energy anytime you can use less electricity or less fossil fuel burning, because that's where the electricity has to come from somewhere. And sometimes it's not a renewable source. So turn off your lights. Improved appliances, something that's more efficient, upgrading what you have, just like the state has to do with different things, with different types of appliances. And then something in societies that we can do is to change how we manage, change how much we're utilizing those greenhouse gases in transportation or industry. And let's try to do something called carbon sequestration. And what that means is the carbon is captured and stored in plants. So let the plants absorb the carbon, if you will, and that can help offset how much GHGs are out there. So some of this is something you can do on your own, and some of it we all have to work together.
Wonderful. So there's not one quick fix. It's going to take everybody's efforts on multiple levels.
Yep, that's true.
All right. Well, thank you very much, Alyssa, and thank you everybody who joined us today. For more on water in California, you can always visit our webpage, water.ca.gov. And if you want to learn more about climate change, we have a water basics page on climate change. It's just a good overview of why climate change is happening and some of the things we can do about it. And then there's also the program that Alyssa oversees, and that is under water.ca.gov/programs, all-programs, climate or /climate-change.program. And you don't have to memorize these. You don't have to write them all down right now. We'll drop them into the comments box on our YouTube channel when we post the video afterward. We also have some educational resources for K-12 students, and you're welcome to visit our water.ca.gov/education-materials page to order any of these. They're all free for students in California. We have materials on climate change. There's a really great poster with ideas for things that school kids can do to help take action to mitigate climate change. And then we also have some workbooks on floods and flood preparedness, because as I mentioned at the beginning of the program today, Flood Preparedness Week is coming up next week, and there's different things that you can do, both again like climate change, personally and in your community, to help be flood ready. We will be back next Wednesday at 1 p.m. with Connie Perkins. She's joining us from our Division of Flood Management, and she'll be talking more about preparing for floods and how you can keep your home, your family, and your pets safe. I want to thank everybody for joining us again today. We hope you have a good week, and we'll see you back here on the 21st. Take care and bye-bye.